Today we are going to discuss the relation between the Young's modulus, rigidity modulus and Poisson's ratio, that is relation y, n and sigma. Now continuing with the previous session, that is the relation between the shearing strain, elongation strain and the compression strain. The same concept we continue. Consider a cube of the side A, P, S, D. On that one, the lower edge ds is fixed. Now we apply a tangential force on the upper side. Due to this, the tangential force, the point A shifts to A dash and similarly P moves to P dash by making an angle theta. So this angle is very small angle we can say. Then a new diagonal dp dash, we can say this earlier diagonal was dp, now it is dp dash. So there is an elongation in the diagonal dp dash. Similarly the diagonal as, so there is a contraction, now it becomes a dash yes. Now draw a perpendicular on diagonal dp dash from P, it will meet at x. Similarly a dash y. So this P dash x, it is the extension which is along the diagonal, the elongation, and ay we can say it is a contraction. Now to continue, when we apply the tangential force, so the shearing strain occurring along AP, the shearing strain which is occurring along the AP due to this tangential force, it can be resolved into two components. The first one is the longitudinal strain along diagonal dp dash, the longitudinal strain along dp dash, so which we call it as denoted by alpha. Similarly, an equal the lateral strain along diagonal a dash s, from a dash s, the lateral strain which we call it as beta, where alpha is nothing but longitudinal strain coefficient and similarly this beta is nothing but the lateral strain coefficient. Let T be the applied stress. Now the extension produced for the length dp due to this tensile stress, the extension which is produced due to dp along the diagonal dp due to the tensile stress is given by the applied stress T into dp into alpha, that is longitudinal strain coefficient. Similarly, the extension produced for the length dp due to the compressive stress is given by T into dp into beta, that is the lateral strain coefficient. Now the total extension along dp, along the extension along the total extension along the dp, so it can be written as the total extension is dp is common into T into bracket alpha plus beta, that is sum of the longitudinal strain coefficient and lateral strain coefficient. But the total extension produced from the diagram we can observe the total extension produced is P dash x. So P dash x is the extension which is produced along the diagonal, the dp dash. So practically the total extension produced is P dash x. Therefore this P dash x is now we are equating to this. Okay, that is P dash x is equal to dpt into alpha plus beta. Now this P dash x is equal to root 2 into L into T alpha plus beta. This is from the previous equation what we have derived. that we have taken it as equation 3, the previous equation. Now from the equation 4, this is also from the previous case, so p dash x is equal to pp dash by root 2. So we can observe here p dash x is equal to pp dash divided by root 2. Even this we is derived from the previous equation, that is nothing but x by root 2. So p dash x is equal to x by root 2. Now making this RHS, that is root 2l into t alpha plus beta is equal to, so p dash x is x by root 2. Now rearranging this term and simplifying, we get 2 into alpha plus beta is equal to x by tl. Now inverting the equation, the above equation, we get 1 by 2 into alpha plus beta is equal to tl by x. So this tl by x may be written as t divided by x by l. So this is nothing but t divided by x by l is equal to theta. So this also from the previous case we have taken into account, that we can see here. So in this, the diagram, the triangle p dash s, so this side is l and this is x, so this is x by l, so that x by l may be taken as theta. Therefore the x by l is equal to theta. So here the x by l will represent by theta, that is nothing but n, that is rigidity modulus. Therefore this n is equal to 1 by 2 alpha plus beta. So once again some rearranging the terms here, many more terms we are going to rearrange. So the RHS may be written as 1 by 2 alpha, if you take out here it will be 2 alpha into bracket 1 plus beta by alpha. In the next case, so this alpha goes to the numerator, it may be written as 1 by alpha into bracket 2 into 1 plus beta by alpha. So beta by alpha is nothing but sigma. So this is nothing but the Poisson's ratio, where beta is lateral strain coefficient and alpha is longitudinal strain coefficient. The ratio of these two is nothing but the Poisson's ratio. So we call this as equation number 7. Now coming back to the basic definition of the Young's modulus, y is equal to stress by longitudinal strain. So this may be once again rearranged, it may be written as 1 by longitudinal strain divided by stress. Numerator comes into denominator. Now this may be taken as 1 by the strain along the diagonal dp per unit stress, so which is nothing but 1 by alpha, that is the ratio of strain, that is strain divided by the unit stress. So that is nothing but the alpha, which is nothing but the longitudinal strain coefficient. Therefore 1 by alpha is nothing but the Young's modulus in the above equation. This 1 by alpha is equal to Young's modulus. Now this equation 7 may be once again written as n is equal to 1 by alpha is y divided by 2 plus sigma, or rearranging the terms we get y is equal to 2n into 1 plus sigma.